Hi, everybody. Welcome to the December Sci-Cafe. I know people are still coming on. Wanted to introduce our speaker and our staff and the series. This is the Sci-Cafe virtual series, and the Apalachicola National Estuarine Research Reserve hosts this Sci-Cafe presentation once a month. Generally, it's the fourth Thursday of the month from 3 to 4. We bumped it up in December because of obvious reasons. This series, we try to offer information about the different studies and scientific studies being conducted in and around Apalachicola Bay in an informal setting, and helping to bring residents and scientists together to learn from each other. The program is going to be about an hour in length with plenty of time for questions, and so feel free to type your questions in the question block, or you can raise your hand, come off mute. We're not that formal when Ethan gets finished. So without further ado, I'd like to introduce Ethan Bourque, our speaker, and he's going to talk about Apalachicola Bay water quality and weather over the last 2 decades. And I also introduce Alicia Bruno. She's our producer of our event, and she's going to be helping us with questions. And I'm Anita Grove. Alicia and I work with the Coastal Training Program section of the reserve. So take it away, Ethan.
Thank you. Afternoon, everyone, and thank you for tuning in today to hear about what is water quality and why does it matter. More specifically, I will be talking about how Apalachicola Bay's water quality and weather has changed over the last 2 decades and why it matters. But first, my name is Ethan Bourque, and I am originally from Rhode Island. I have been monitoring various forms of water quality for about 20 years. Before moving to Florida, I had worked on several successful oyster reef restoration projects and managed a 10-acre oyster farm. Then about 9 years ago, I started working here at the Apalachicola National Estuarine Research Reserve in the research section as a water quality researcher. Today's talk agenda, the main points I'll be covering are why estuaries matter, what are the NERRs and SWAMP, highlights from the 2022 Research Reserve Report, how the estuary is changing, long-term weather and water quality trends, and the new product for the reserve. Why estuaries matter. Here are just a few of the many reasons why estuaries are important. They have economic impacts, community benefits, healthy ecosystems, provide recreational and commercial opportunities, and habitat diversity. National Estuarine Research Reserve, tracking the health of our estuaries 24/7. The National Estuarine Research Reserve System is a partnership program between NOAA and the coastal states to manage designated reserves. More than 1.4 million acres of estuarine land and water are protected. Each reserve is managed on a daily basis by a lead state agency or university with input from local partners. The health of every reserve is continuously monitored by the system-wide monitoring program. SWAMP is a robust, long-term, and versatile monitoring program that uses the NERRs network to intensively study estuarine reef reference sites for evaluating ecosystem function and change. Reserve-generated data and information are available to local citizens and decision makers. Here's a map of the Apalachicola, Chattahoochee, Flint River Basin. It is a roughly 19,800 square mile drainage basin or watershed of the Apalachicola River, Chattahoochee River, and Flint River. It starts in the mountains of northeast Georgia, drains much of West Georgia, southwest Georgia, southeast Alabama, and the central part of the Florida Panhandle before flowing into the Gulf of Mexico here in Apalachicola. The Apalachicola National Estuarine Research Reserve is one of the most productive estuarine systems in the Northern Hemisphere. The economic, recreational, educational, and environmental benefits provided by this estuary are enhanced and protected by the programs and initiatives led by reserve staff. The reserve encompasses 2 barrier islands and a portion of a third, the lower 52 miles of the Apalachicola River and its floodplains, portions of adjoining uplands, and the Apalachicola Bay estuarine, riverine, and floodplain systems. And this is a map of boundary with a few of our stations. The Apalachicola Bay system is a wide, shallow, river-dominated estuary. The estuary's primary source of freshwater and nutrient loading is the Apalachicola River, which is Florida's largest river in terms of volume of flow. Characteristics of the Apalachicola River include heavy sediment load, turbid water, and substantial annual flooding. Seasonally, summer and early fall are characterized by low flows, with the highest flows occurring in late winter and early spring. The health of every reserve is continuously monitored by the NERR's System-Wide Monitoring Program, or SWAMP, pronounced SWAMP. The goal of SWAMP is to identify and track short-term variability and long-term changes in the integrity and biodiversity of representative estuarine ecosystems and coastal watersheds for the purpose of contributing to effective national, regional, and site-specific coastal zone management. To do this, reserves collect water quality data every 15 minutes using automated data loggers, monthly nutrient sampling, and weather data every 15 minutes. What is water quality? Well, that's a complicated question. Water quality can be thought of as a measure of how suitable the water is for a particular use based on selected physical, chemical, and biological characteristics. Although scientific measurements are used to define water quality, it is not a simple thing to say that water is good or that water is bad. This is because the determination is typically made relative to the purpose of the water. For instance, water quality that would be considered bad for drinking could be fine for industrial use. Here at the reserve, we monitor water quality by measuring these physical, chemical, and biological characteristics or parameters. Here are the highlights from the 2022 annual reserve level report based on data collected by the research section's staff. It was hotter, drier, salinity was below the long-term historical average, and dissolved oxygen decreased. So how is our estuary changing? Well, it is warmer, drier, and there was less dissolved oxygen, and the average salinity of all water quality stations did not change. Here's a graph of long-term trends. This trend plot of 21 years of weather and water quality data at all primary swamp stations. At the top, you can see the trend information for our weather station. Below that are the trends of our water quality stations, followed by nutrient station trends. Weather is what you see outside on a particular day in terms of precipitation, temperature, humidity, cloudiness, visibility, and wind, while climate tells us about the average daily weather for an extended period of time, years, decades, centuries, at a certain location. On this slide, we have the daily average air temperature for 2022, historic daily range, and historic average daily range plotted. Notice the large variability in the daily average. On this slide, notice how much less variable air temperature is for 2022. This is because the occasional daily extremes have less of an effect on the average air temperature as the time scale increases. Another thing to note is how the 2022 daily average air temperature was slightly warmer from February through July and in September and November compared to the long-term historical average. Also, look at how much higher the low end of the daily average range was than the historical range in every month except October. Local climate, air and water temperature are both increasing over time. Water temperature stayed about the same from 2001 to about 2007, then increased 1 degree Celsius, roughly 1.8 degrees Fahrenheit, by the end of 2022. Over the same 21 years, air temperature decreased from 2001 to 2008. Then by the end of 2022, it had roughly increased by 1.2 degrees Celsius, or roughly 2.2 degrees Fahrenheit. This is important because as water temperature increases, the amount of dissolved oxygen it can hold decreases, and aquatic organisms require dissolved oxygen to survive. During the hot summer months, dissolved oxygen levels can be further reduced by algae blooms leading to fish kills. On this slide, notice how dissolved oxygen is the lowest during the hottest months. Also, that red dashed line is the hypoxic threshold, and it indicates the point where dissolved oxygen begins to be insufficient to sustain bodily function. This is a map of the water quality stations, and it shows that dissolved oxygen has decreased at East Bay surface and bottom and dry bar stations. Most of the measurements vary between poor and good range at all locations. On this slide, there are a few very important takeaways. The graph in the upper left shows that as temperature increases, oxygen decreases. The graph in the upper right shows that the relationship between oxygen and pH is such that if one increases, so too does the other. This also means that if one decreases, so does the other. The graph on the bottom left shows that dissolved oxygen in the bay has decreased over time. And the graph on the bottom right shows that pH has decreased over time. In fact, it has decreased by 0.2 over the last 21 years. Now that doesn't sound like much. However, because the pH scale is logarithmic, this means that the acidity of the bay has quadrupled. As pH decreases, the amount of carbon dioxide in the water increases, increasing its acidity and causing carbonate ions to be less abundant. The decrease in carbonate ions can make building and maintaining shells in other calcium carbonate structures difficult for calcifying organisms, such as oysters, clams, sea urchins, crabs, and coral. Although some species are able to compensate for this, the process is energetically expensive, and leaves less energy for growth and reproduction. On this slide, the graph on the left shows that in 2022, local rainfall was about 15 inches less than in 2021, and about 2 inches below the long-term historical average due to a drier summer and fall. If we look at 2017 and 2018, we see that the yearly totals are very close to each other. However, 2018 received most of its rain in the summer and virtually none in the winter. On the right is a graph of Apalachicola Bay river flow by year, and it has red lines on it for when the dam was installed, the flood in 2005, and the drought in 2012. This graph also shows that river flow has been decreasing since roughly 1975. Now let's look at local rainfall during the flood of 2005 and the drought of 2012. During the 2005 flood, local rainfall was about 4 inches below average. During the drought of 2012, local rainfall was about 2 inches above average. This means that upstream rainfall has a larger effect on river flow than local rainfall does. To drive this point home a little bit more, this slide has yearly precipitation by season and includes a seasonal average bar. Looking at the summer of 2005, we see that despite the flood, local rainfall was well below average. Turning our attention to the seasons of 2012, drought, we see that local precipitation was a little below average in the winter, well above average in the spring, slightly below average in the summer, and below average in the fall, which is the driest season. The Apalachicola Bay is a river-dominated estuary, as shown by the strong correlation between river flow and bay salinity. This means that upstream rainfall has a greater influence than local rainfall on bay salinity. Primary production in the bay tends to be fueled by nutrients coming from upstream river flow. However, river water is high in tannins from the decay of wood, bark, leaves, and fruit within the watershed, and it stains the water dark like black tea, which reduces water clarity, limits plankton growth, and is why chlorophyll levels increase during dry season, summer, early fall, and decrease during the wet season, late winter, early spring. River flow is the primary driver of salinity in the bay, meaning that salinity increases with distance from the river mouth. Researchers found that the estuary can be characterized into 3 distinct regions by differences in salinity. These different regions can be seen on the map as upper stations, middle stations, and lower stations. From 19 years of biological monitoring data, they also found that seasonal differences in salinity drives where shrimp, crabs, and fish communities are distributed within the bay. Distribution of these communities was found to be more pronounced during the spring, summer, and fall seasons, with more overlap between communities during winter. As part of the NERR's system-wide monitoring program, research staff have been tracking 24/7 the health of one of the most productive estuarine systems in the northern hemisphere. From their tireless work, we have learned that the Apalachicola Bay is a river-dominated estuary. The Apalachicola River is the primary source of nutrients for the bay. River flow is the primary driver of salinity in the bay, and seasonal differences in salinity drives the distribution of species communities within the estuary. Air and water temperature is increasing. The dissolved oxygen that aquatic organisms need to live is decreasing. pH in the bay is decreasing, and it is becoming more acidic. Now, before everyone starts canceling their beach plans, the change in acidity is imperceptible without instrumentation. But as pH decreases, the amount of carbon dioxide in the water increases, increasing its acidity and causing carbonate ions to be less abundant. This decrease in carbonate ions can make building and maintaining shells and other calcium carbonate structures difficult for calcifying organisms, such as our very important oysters and crabs and coral. Although some species can compensate for this, the process is energetically expensive and leaves less energy for growth and reproduction. On this slide, on the left-hand side, you can see the cover picture for the reserve level report, which is a new tool that the NERRs are using to help answer frequently asked questions, like how is the Apalachicola estuary changing, and how is the Apalachicola Bay water quality. These reports are generated annually using the swamp data that the research section collects. Please stay tuned as we work to have these annual reports added to the Friends of the Reserve website. Thank you very much and for joining us today and listening to my talk about water quality. Anita, Alicia?
Yeah. Thanks, Ethan.
We open the floor to questions.
Yeah. We appreciate it. Thanks so much for your talk. And Alicia's gonna pace us through questions.
We're still waiting for some to come in.
While we're waiting, I have a couple. If I may have missed something, but see if I can find where did I put it. I think you kind of touched on this, but the reason dissolved oxygen is important. I know after Hurricane Michael, we saw a huge fish kill, and a lot of people attributed it to the water being polluted, but we later found that that was actually because of the dissolved oxygen was so low from all of the water coming in and rushing upriver. So mainly it was the dissolved oxygen and why we measure it, because it's important to the
it's an
health of the fish.
Important indicator of the health. I mean, if there's no oxygen in the water, there's not going to be any life in the water. And for Hurricane Michael, when it hit, it stirred up the bottom and made the nutrients that had settled out into the mud and the muck available again. And so all those nutrients that suddenly became available, plus what was coming down the river from all that rain that washed everything into the river, it was just an explosion of activity. And we ended up having anoxic conditions because of it.
Great, thank you. And I'll ask another one. In your you've said you've been here 9 years. What do you think the most notable change you've seen take place in these water quality parameters?
I'm not, I didn't notice it until I had time to start really digging into the data, but the water temperature has been rising, and I'd have to say water temperature.
Great, thanks. And I noticed you had the East Bay station and the Cat Point station. There was a difference in, was it available? What was that? Temperature, I guess, or dissolved oxygen? Is that due to the depth of the water?
So
That was back where you showed the stations.
on this one, how it's changing,
Yeah, and that one.
I don't know exactly why. Cat Point is the one station that the DO has increased. It could be related to salinity. At Cat Point, you have higher salinity values than you do at East Bay or at Dry Bar. But depth-wise, Cat Point and Dry Bar are fairly similar.
Oh, okay. Right.
At least at the depth at our monitoring stations. There is a very sharp drop off at Cat Point.
If anybody wants to come off mute and ask a question, we'd love to hear.
So we have a question from Barb Shoplock. They want to know, are you using any citizen or community science programs to help with monitoring? If not, can you think of how you might?
So for the swamp program, citizen science isn't part of it, but we are using citizen science for our microplastics. And we have a that goes out. Offhand, I don't know the frequency, but they collect water samples and sediment samples throughout the Apalachicola Bay watershed. And they bring them back and they process them and have been doing so for, I want to say, the last 3 years.
Barb says thank you. And then Tom Dolan has his hand up. Tom, if you'd like to come off mute and ask your question, go right ahead.
There we go. Okay, great. I was curious. You said that it's a river-driven system, which is pretty clear from what you presented. What are the outflows of river input relative to sort of East Pass, West Pass, and Sykes Cut? Do you have any idea?
I'm sorry, Tom, you were breaking up a little bit. Did I hear you correctly that you were asking about flow through Sykes Cut?
Yes, flow through Sykes Cut or the East or West Pass. If it's a river-driven system, do you have any information about what the flows are through those gaps, if you will?
I do not have any of that, but
okay.
I'm sure it has been looked into. But
yeah, I realize that. Yeah, I realize this wasn't the topic of your talk, but I was just curious that if you were to close Sykes Cut, for example, what would you expect? What would you expect to see with respect to some of the parameters that you've got, as far as salinity goes, as far as temperature of the water goes, as far as dissolved oxygen goes? Is there information there about what might happen?
I'm not exactly sure. I do know that from all the time I've been here, the Gulf water flows in from the east, and so along the barrier islands, unless the river is really pumping, it is pretty close to full strength Gulf water.
Oh, really? Okay. Okay.
So the river isn't really, fresh water isn't really showing up too close to Sykes Cut unless the river flow is exceptionally high.
Oh, okay, great. Thank you.
Mm-hmm.
Great question, Tom. I know we hear that a lot. People think that if we close the cut, that all the problems would be over. And I think some of our data kind of shows it's more complicated than that. So I want to thank everybody. Go ahead.
That's what I figured. Yeah, that's what I thought. I was curious because you hear people talk, like you say, about that all the time. And I was just wondering if it could be a comment based on what we've seen. And I suspect.
Yeah.
Again, thanks, Ethan.
You're very welcome, Tom.
I want to thank everybody for showing up and asking questions. We appreciate it. Ethan, thank you so much for your wonderful talk, and look forward to seeing more information on our water quality reports. So we will have our next Sci-Cafe on January 25th. So be sure to join us, and I hope everyone has a wonderful holiday. Thank you, Alicia, and thank you, Ethan.